This is the explanation on the first project. The title of the project is Threads. In this project, we're gonna implement three main topics. First one is alarm clock, second one is priority scheduling, and the third one is advanced scheduler. The first topic is alarm clock. We're gonna modify the system called timer alarm. And system called timer alarm is a system call that wakes up a process and takes a amount of time. Pintos currently uses busy waiting for an alarm, and we're going to modify the Pintos OS to use sleep and wake up paradigm for alarm. This is how timer sleep is implemented in current Pintos. In current timer sleep implementation, the process switches between ready state and running states to check if the alarm time has come or not. And as a result, it only uses two states and it keeps crunching the CPU instructions, waiting for CPU cycles. From data structure's point of view, the thread is put into running mode, and if it calls alarm, then it puts itself back to the end of the ready list, and then it executes again. So basically, in timer sleep implementation, it keeps executing this loop. This is how the timer sleep is implemented. If you look at this code, then first, when the timer sleep is called, it records the current time. And then within the while loop, it keeps executing the thread yield. So it releases CPU, and then when it has put into the running state, it checks the time. If the elapsed time is less than ticks, then it releases CPU again. So basically, the process that calls timer sleep switches between ready state and running state. Let's look at the details of thread yield. It is worth looking at the details. First, it gets the pointer to the current thread structure. And then it disables interrupt. And then it puts the current thread structure to the end of the ready list, and then it changes the state of the currently running thread to thread ready, and then it calls context switch. And then after context switch finishes, it sets the interrupt level back to its original state. This is how the thread yield is implemented. There are 5 essential functions inside thread yield. First one is thread current. It returns the current thread pointer. And then it disables interrupt. And then there's another function which is counterpart of interrupt disable. It is interrupt set level. It restores the interrupt level. And then list pushback is a function that places the given object to the end of the specified list. So the objective of this function is put the current thread structure to the end of the ready list. And then it calls schedule to do context switch. The objective of this project is make the timer sleep more efficient. We're gonna introduce the block state, and then we're gonna implement the timer sleep using blocked state. So when a process calls timer sleep, the operating system puts itself to the block state. And then operating system is responsible for wake up the blocked process, frequently checking the timer interrupt. Using this approach, the operating system can save CPU cycles, and then also, more importantly, it can save power consumption. So, this is the design. There is, as you see at the beginning of the code, there are only 2 lists in current Pintos. First one is all list, and the other one is ready list. Ready list is a data structure that represent a set of processes that are waiting for a CPU to be executed. Now, you are going to introduce a new data structure. This is the list of blocked threads. So it represents a set of threads that are in the blocked state. So When a timer, this is a design, when a timer sleep is called, when a process calls timer sleep, operating system puts the thread to the sleep list. And then operating system keeps checking the timer, and then when timer is up, then it wakes up. Wakes up means move the thread from the sleep list to read list. That's what wake up is for. So this is the design of our timer sleep algorithm. So this is implement details. First, we have to define the sleep queue. So we have to define the sleep list. You can name it by yourself, but you have to define it as a sleep list. And then you have to initialize it, of course. For every data structure, you have to initialize it properly. So the point to think is, where do we put the declaration statement, and when are we going to initialize it? So this part is left to you to implement. In implementing the block-based timer sleep, you have to introduce two things. First one is global tick, and the second one is the local tick. Every time the basic design idea is that every time when timer interrupt handler is executed, the kernel checks if there's any threat to wake up. To do that, it first has to scan the blocked thread list, and then find if any the local tick for the blocked thread is greater than the global tick. So in local tick, each thread maintain the time to wake up. So currently, our thread structure does not have this field. So we have to modify the thread structure and to store the time to wake up. And also, for efficiency's sake, we have to introduce one global variable. It's a global tick or whatever. At your disposal, you can name the variable. It stores the minimum value of the local ticks of the threads. Every time the timer interrupt handler is executed, it checks the tick, the global tick variable, and the current time is less than or equal to the tick. If the current time is greater than or equal to the tick, then it means that it has to wake up some threads in the block list. Otherwise, it doesn't have to scan all the block thread. So the reason we introduced the tick global variable is to save the time to scan the sleep list. So in the data structure, you have to add a new field that represents the alarm time to wake up. And this is the actual implementation of the code. In timer sleep, instead of put itself in the while loop for busy waiting, if the time to wake up is still, the time has left, some time has left, still it has to wake up, then it puts itself into the sleep by calling thread underbar sleep, and then it passes the alarm time it needs to wake up as a start plus tick. There's an interesting property here. It is possible that value of start may become invalid at 2. So because there are context switches in between, and by the time it executes a statement, the time here it has obtained may not valid anymore when executing the line number 2. So we're gonna forget it for now, but if you are a really good system programmer, you may want to think about the way how to fix it. So this is the body you want to implement in the thread sleep function. If the current thread is that idle thread, you have to change the state of the caller thread to blocked and store the local tick to wake up to its thread structure, and you have to update the global tick if necessary, and then call the schedule. And you should not forget to disable interrupt when you insert a thread structure through the thread list. So the important thing in thread sleep is change the state of the caller thread to blocked and put it to the sleep queue. Timer interrupt implementation is heart of everything. In timer interrupt, you have to modify the timer interrupt handler, and inside the timer interrupt handler, the operating system should determine which threads to wake up every time when the timer interrupt occurs. When the threads to wake up, you have to remove them from the sleep queue and then insert it to the ready list. So you are modifying the ready list and then sleep list. So when you modify the sleep list and ready list, you should not forget to disable the interrupt and enable the interrupt before and after modifying the list. And also, you should not forget to change the state of the thread from sleep to ready when you put the threads in the ready list. One thing you might remember is, depending upon how you organize the sleep list, the time to identify the threads to wake up may varies a lot. For example, this is sleep list. And if you organize the sleep list and if you sort the sleep list with respect to the alarm clock time, so this is 10, and this is 10:01, and this is 10:05, and so this block list is sorted with ascending order of the alarm time. So when you want to find the threads to wake up, you can start scanning from the beginning of the queue, and you can stop scanning until you find the last threads to wake up. However, if this list is not sorted, then you have to scan entire list every time you need to find the threads to wake up. This is the modified code for timer interrupt. You have to add this part. So you check the sleep list and then check the global tick, and you find any thread to wake up. And then you move them to the ready list if necessary, and then you update the global clock. So this is simple. So in summary, you have to modify a few functions: thread init, timer sleep, and timer interrupt, to make your timer sleep function based upon sleep and wake up protocol. There are a variety of ways to write your own code, but following the design suggestion for modularization, you might want to add 4 functions. First one is function that sets the thread state to blocked, and then insert it to the sleep queue. The second function is find the thread to wake up from the sleep queue and wake it up. Wake it up means that put the threads from the sleep queue to the ready list. And also you might want to write a function that saves the minimum value of tick that threads have. And lastly, you might want to write a function that returns the minimum value of the ticks. After you writing all the code, you have to check if your code passes the alarm test. So this is the result, and then hope you pass this test. The second topic is priority scheduling. The Pintos uses FIFO scheduling. You are required to modify the Pintos scheduler for priority scheduling. This is the result of what you are required to do. First, sort the ready list by the thread priority. Second, sort the wait list for the synchronization primitives such as Semaphore, condition variables, and locks with respect of the priority. And we also have to implement the preemption. And the preemption point is when the thread is put into the ready list. So it is important that you do not have to check the preemptibility every time when timer interrupt is called. In this scheduling algorithm, operating system check the preemption only when the new thread arrives to the ready list. You have to modify 2 files. So this is the design. When you examine the ready list and select the next thread to run, you get the thread with the highest priority. That's one thing. And then when there are a set of threads waiting for the lock, then when the lock becomes available, the operating system selects the thread with the highest priority. That's the two things you have to implement. There are three things to consider. First, when selecting a thread to run in the ready list, we have to select the one with the highest priority. And when inserting a new thread to the ready list, operating system is required to compare the priority with the running thread, with the existing one. And we have to schedule a newly inserted thread if it has the higher priority than the currently running thread. So that rules apply to the set of threads waiting for synchronization primitive such as locks, semaphores, and condition variable. When the lock becomes available or semaphore condition variable is available, operating system selects the thread with the highest priority. Let us explain the priority in Pintos. In Pintos, the priority ranges from 0 to 63. There are 64 priority levels. And the larger the number, the higher the priority. The default priority is set when the thread is first created, and the default priority value is 31. Pintos operating system currently provides two functions. First one is set thread priority that sets a priority of a thread to a specified value, and then get priority that gets a priority of a given thread. In implementing a priority-based scheduling, we have to modify a few things. The first thing is that when you call inside thread create, we like to maintain this ready list sorted with respect to the priority of a threads in the ready list. So when you insert a thread after creating the thread, you put the thread respect to the order of the priority. So this is going to be very expensive. And the second thing is when the thread is added to the ready list, the operating system has to compare the priority of a newly incoming thread with the one that's being executed. And if the newly incoming thread has a higher priority, then we have to call schedule so that we can switch out the currently running thread and push the newly incoming thread to CPU. So this is the code for thread create. So we have, after unblock the thread, we have to compare the priorities of the currently running thread, compare the priority of the currently running thread and the newly inserted one. If the newly arriving thread has a higher priority, then the existing thread has to give up the CPU. And there are a few others to modify. When the thread is unblocked, so when the thread is unblocked from the ready state, when it puts in the ready state, also insert with the priority order. And then also when a thread calls thread yield, also it has to put itself to the ready list with respect to the priority order. And there's another function we have to modify, that is set priority. Set priority function changes the priority of a thread with a given private value. In current Pintos, thread set priority function just simply set the priority with a new priority value. But in the new function, in the new modified algorithm, thread set priority not only sets the priority value, but also adjusts the location or position of the thread within the ready list. Because ready list has to be sorted with respect to the priority value of the threads in the list. We're going to show the details of how we can modify the thread unblock code. When unblocking a thread, we are going to place the thread on the ready list with respect to its thread priority. In the existing code, operating system puts the unblocked thread at the end of the ready list. like this. List underbar push to back. So we delete this code and we put the newly unblocked thread in the ready list with respect to the priority. And we have to change the synchronization primitive. There are lock, there are semaphore, and there are condition variables. And when the lock or semaphore, the condition variables becomes available, we have to make up the waiting thread. We have to wake up the waiting thread with respect to the thread priority. This view graph shows how the lock is maintained in Pintos. Pintos operating system uses first in, first served in determining the lock holder. There are assumed, let's say there are 4 threads, A, B, C, and D. And A is currently holding a lock and continues executing until this point. While A is holding a lock, B has made a request first, and then D has made a request next, and then C has to make a request third. After A releases a lock at this time point, then operating system decides the thread to acquire the lock. There are 3, by this time, there are 3 threads waiting for the lock. There is B, and this is D, and this is C. Among these 3 threads, D has the highest priority. However, even though D has the highest priority, the operating system just removes the first thread in the list and assigns a lock. So the order in which the lock is acquired is from B and D and C. So between B and D, there is priority inversion. The process with the higher priority is waiting for the process with the lower priority. That's because this happens because Pintos uses FIFO lock-unlock mechanism. In priority-based lock-unlock mechanism, the waiters acquire the lock based on this priority. This is the same example. There are 4 threads, A, B, C, and D. And B has made a request, and then D has made a request, and then C has made a request for the lock. But after A has released the lock at this point, there are 3 threads, and different from the previous slide, the waiting list here is ordered with respect to the priority. So when thread A releases the lock, the thread with the highest priority, thread D, gets the lock. And then after D releases the lock, the thread with the next highest priority, thread C, gets the lock. And B is the last to get the lock. We are going to briefly introduce the basic functions in Semaphore and condition variable, and going to point out what kind of functions we have to modify in Semaphore and condition variable. In Semaphore, there are 3 functions. First one is sema-init, which initializes a semaphore to a given value. The second one is sema-down. It requests for a semaphore, and if it is acquired, then the process proceeds. But if the process fails to acquire semaphore, then it has to block. And sema-up releases the semaphore. So here you have to modify sema-down and sema-up. In the lock, there are 3 functions: lock init, lock acquire, and lock release. But as you can see, lock is implemented by the semaphore. So in order to modify the lock primitive based on priority, it is sufficient to modify semaphore. A third function is condition variable. There are 4 important functions in condition. First one is init, which initializes the condition variable data structure. Second one is conwait. Once a process calls conwait, the process is put to the block state and it waits for a signal by the condition variable. And third one is signal. It sends a signal to a thread of the highest priority waiting in their condition variable. And then there's another function, broadcast. It sends a signal to all threads waiting in the condition variable. This is the functions to modify. There are two functions you have to modify. First one is semadown, and the other is can't wait. So inside this code, you are required to modify the code so that when the process is put into the wait list, they have to be sorted with respect to the priority. And also you have to modify a sema up and can signal as well as set priority so that all the lists can be ordered with respect to the priority. There are important issues you have to consider. First one is priority inversion. Priority inversion is the one that a higher priority process is waiting for the process of the low priority. Consider this situation. There is three thread A, and there thread B, and thread C. And A is executing, and it has acquired lock at this point. Then it continues executing, and C is asking for a lock, but it is being held by A. So A is executing, and C is blocked from this point. But at this point, A have been executing until this point, and then B has arrived. Because B has a higher priority than A, B gets executed while A gets into the red list. And then there's interesting thing happens. Because currently C is being blocked because waiting for A. However, A hands over the CPU to B because B has higher priority than A. The problem is the relationship between C and B. C has the higher priority than B, but it turns out that C is waiting for the B to finish. This is called priority inversion. So, in our priority scheduling, we have to fix this problem. In 1997, Pathfinder on Mars has stopped because OS operating systems crashed due to the priority inversion. The engineers in NASA has downloaded their source code of Pathfinder, and they identified that the crash was occurred due to the priority inversion. And then they find the cause, fix the system, and upload the code to the Pathfinder and make it work. This is the interesting story and importance of the priority inversion. There one thing you'll use to fix the priority inversion problem. This is called priority donation. Priority donation is the action of inheriting the priority of a process to the lock holder. Let's say there are three threads, again, thread A and thread B and thread C. A is executing while holding a lock at this point. And then A is executing. And at this point, the C is asking for a lock. But lock is being held by thread A. At the time, if you compare the priority of C and A, then A has low priority. So when C is asking for a lock and finds that A is holding a lock, then C inherits its priority to A, so that A's priority gets boosted to C's level. Right after A's priority has been boosted from lower level to C's level, you can see that B has arrived at the system. In the original scheduling algorithm, B is supposed to preempt the process A. However, in this case, process A's priority has been boosted to C's level, so there is no way for B to preempt process A. So the process A continues executing at the C's priority level, and once it's over, then the lock is handed over to process C, so process C gets executed, and then after process C finishes execution, it releases the lock, and then process B finally gets an execution opportunity. So via donating priority to the lock holder, we avoid priority inversion. This technique is priority donation. In the system without priority donation, there is a lock, And this is lock is currently allocated to thread 1 with priority 10. And after thread 1 acquires the lock, 3 thread has arrived: thread 1, thread 2, thread 3, and thread 4. Each of these threads has priority 9, 12, and 8. Without priority donation, the priority of thread 1 remains as 10. But if we employ priority donation, then the lock holder's priority becomes a priority of the highest priority threads. So here there are three threads, T2, T3, and T4. And T2 has the priority 9, and T3 has priority 12, and T4 has priority 8. So among these threads, thread 3 inherits its priority to thread 1. This is priority donation. There are a few issues to consider. First one is nested donation. Consider this scenario. There are 3 threads: thread 1, thread 2, and thread 3. And thread 1 has priority 10, and thread 2 has priority 9, and thread 3 has priority 7. Somehow, first, thread 1 is holding a lock A. And then thread 2 has made a request for thread lock A, and it's got blocked. However, thread 2 is holding a lock B, and thread 3 is waiting for a lock B to be released while holding lock C. So there is a chained lock holding relationships. What if there comes a thread 4, it has thread 14, and it issues lock C? Okay, and then thread 4 is make a request for lock C, and then because of the priority donation, it will donate its priority to its lock holder T3 and make the priority of itself to 14, 7 to 14. However, here T3 again donates its priority to its lock holder. So the priority of T2 is updated from 9 to 14. Again, T2 inherits its priority to its lock holder, and it inherits priority 14 to its lock holder. So the priority level of T1 is updated from 10 to 14. This is called nested donation. So in your priority donation implementation, you have to implement the nested donation feature in your priority scheduling algorithm. Next topic is multiple donation. Thread 1 is holding 3 locks: lock A, lock B, and lock C. The original priority of thread 1 is 10. T2 makes a request for lock A. Its priority is 12. So the thread T1 is donated the priority of 12. So 10 changes to 12. And then T3 make a request for lock B, and then it has a priority 11. So it does not donate its priority to its lock holder because the current priority that has been donated by T2 is 12. Now T4 make a request for C, and T4's priority is 13. So priority 13 that has been held by T4 is larger than priority 12. So finally, the priority of T1 becomes 13. Let's assume that T1 has unlocked the lock C. And then as a result of unlock lock C, the lock is really allocated to T4. But then after releasing lock C, T1's priority should not become its original priority 10, but the priority of T1 has to be updated to the largest priority that donated the priority to T1. So here, priority of T1 now become 12. That is multiple donation. So in your priority donation mechanism, you have to implement a nested donation and multiple donation. The idea is simple. For supporting multiple donation, thread has to maintain the list of donors. So every time it releases lock, it searches the donors and get the highest priority of the remaining donors. For nested donation, you have to maintain the lock that it waits for. And then once you inherited a priority, you have to check if you need to inherit the current priority to your child. That's the way you implement a nested donation. This is the functions you modify in priority donation. You have to modify the init thread data structure, and you also have to modify lock acquire and lock release and set priority. In lock acquire, if the lock is not available, you have to store the address of the lock. You have to store the current priority and maintain the donate threads on the list. And then you all have to donate the priority. When the lock is released, you have to remove the threads that holds a lock on the donation list, and you have to update the priority properly. And also, when you set the priority, you have to set the priority considering the donation. So that's the issues you have to modify. And this is the result of the test.